Good morning, everyone. So last lesson we studied a little bit about the Maxwell equations in matter and in vacuum, and today we are going to continue with that. But what I'm going to introduce more deeply is the concept of energy of the field, and this will lead us eventually maybe 2 more lessons to the concept of radiation. So now we want to actually deal with conservation laws. I'll focus mainly on energy, but also momentum. So the energy in electrodynamics is very special in my mind. It is very different than what you are used to in mechanics. And you need to think about it deeply. It's very deep. It's a very deep theory, and it's very strange, at least at the beginning, and you need to think what it means. The reason I'll demonstrate with a simple example. So, okay, so someone asked me what do we study in this class. So this, I think, is chapter 8. So what I'm not, this is minus stress tensors. So it's all of chapter 8 except for stress tensors. Why do I mention then stress tensors? Because next lesson we're going to study stress tensors. Stress tensors are very complicated mathematically, in my opinion. So better read about it for next lesson. I'm also not going to follow Griffiths exactly. You'll soon see in what sense. He uses a discussion on energy by looking at the vacuum with the current J. I will look at it with free charge. So it's actually what I'm doing today is an exercise at the end of the chapter 8, where you do it in matter. I solve this because that contains in it the other case, which is for the vacuum. I'm also going to discuss a little bit today already about chapter 9, and that is the connection of electromagnetism with light. So it's a mixture. Then I'll go back to the stress tensor. So again, I want you to read about it, and then it will be and then I'll continue with chapter 9 later on, of course. Okay, and yeah, I don't think this lesson is particularly following Griffiths. So yeah, you better read Griffiths deeply. Okay, so let us start the discussion, and I want to start it with a very simple example. I asked ChatGPT, and I thought, what is the simplest thing to introduce this concept of energy? And I want to solve a problem that you can solve in high school. And we can solve it in high school very easily, but then we have to think what's going on. And I think this leads to some interesting ideas on this concept of energy of an electromagnetic field. So I have 2 plates. And one of them is charged with charge minus sigma. This is not conductivity, this is charge per unit surface. I'm going to think about them as being very big. The surface area is A. So this is going into the wall, that's the surface area, and we have this D. This will be the initial condition. Furthermore, these charges are going to be fixed. I nailed them. They cannot move, they cannot produce currents, etc. And this one I'm going to take, I'm going to fix it. So this one is going to be fixed. Now, if you have a minus charge on this one, you have a plus charge on this one, what will happen to this guy? It will experience a force, it will be attracted to these plates will be attracted, right? And it's going to be very simple. We're also going to calculate it. So we are starting this one from rest. It's not moving at the beginning, and it can move towards, it's attracted, this plate can move to this plate. And to calculate this is very easy. We'll do that with basic Newton's law. And what we will ask, so what will happen? It will accelerate, right? And just before hitting the wall, it will have some velocity. Everyone agrees? What does it mean it has velocity? It has kinetic energy, right? This wall. where does the kinetic energy come from? So again, you start here. At the end of the experiment, I'll have this situation. They're very close. Now you start at 0 kinetic energy, but now you have some kinetic energy which we can calculate. Where does it come from?
Electric potential.
From the where?
Electric potential.
Okay, electric potential, you need to define it a bit more carefully. So the bottom line, and this is what I want to show, is that inside here there is an electric field. This is the usual electric field between these two plates, right? This electric field has a density of energy. So if I look at some point here, there is some energy in this part in space. So if there's an electric field here, when I look at space and even there is nothing, I can talk about some energy density at this point. So what is going to happen? At this stage, we have some energy related to the electromagnetic field here inside. By the way, what is the electromagnetic here and here is going to be 0 and 0 because of this is plus and this is minus, right? So there is going to be some electromagnetic energy due to the density of electromagnetic fields, density of the energy here, and this will disappear. And if we believe in conservation and energy, and we can believe many things, you can even believe me sometimes, but you always believe conservation of energy, this change of energy should be the same as this kinetic energy. Okay, so this is what we are going to calculate now, and it's true, it's the same. And we don't need the concept of conservation of energy to calculate this kinetic energy, because this you can do also by Newtonian mechanics. It's very simple, actually. In this case, there is no need to think about the energy of the stored in here. But why we should think about it and think about it very deeply, because this will come later. Okay, so here I'm reducing the space where the electric field is done, and I do this by moving this thing. But I can change this density by many ways. For example, I can have currents, or I can change the charge here and suddenly create some energy, or change the energy density here. So by time-dependent fields, that will be way more complicated. Later I can play with the energy. I can have a spot, this spot for example, it has some energy density, and I can increase it and I can decrease it by controlling currents, controlling densities, whatever you want. And then then we start facing the question of, okay, let's say in this point I change fields, and then let's say the energy inside here is reduced or increased. So something has to flow inside. If you have some energy, then something is going in and something is going out, like conservation of mass, conservation of students, etc. I mean, the energy is not created so something is flowing out and something is flowing in, which is energy, and the energy density at the point is changing. This is going to be these conservation laws that I'm going to discuss about, which are formed in a kind of continuity equation, but it's a new continuity equation. It's a continuity equation that is given for the fields. Now, energy is complicated because there are different types of energy, as you know. There is, for example, there is kinetic energy that I discussed here. There is heat. So if I have a slab and I have some electromagnetic field, so I create heat. Heat is, of course, some form of kinetic energy, but we call it heat because of we cannot control it. We don't see the microscopic. We can change it into mechanical energy. We can change it into radiation energy. Eventually, that will be the most important, because with radiation energy, you know, it's not only that you go to the beach and you are hit by some electromagnetic wave and you get burned. It's also that you change information in your cell phones. So essentially all the modern world is built on this change of energies and transformation of energies from electromagnetic fields to radiation, but sometimes it's to kinetic energy or to many things. Okay, so we need to think about these type of questions. And let us start with a very simple exercise to do that, and it will be also a reminder. So let us think, what is the field here inside? So there are two aspects of the problem. What is the force on this plate? And the other thing, what is the E inside? There is a small catch here that you need to be a bit careful in calculating. So
we're talking about the classical capacitor propagator. Capacitor, when a changing field inside the capacitor creates an external electromagnetic wave.
No, I'm talking about the most trivial problem. I'm talking about you have a plate, but it is, you are right that it is a capacitor. There's no wave here, there is nothing. There is one plate with charge sigma and another plate with charge, sorry, this one is minus sigma, this one is sigma. And this plate is exerting force. It's not a capacitor that is held fixed. So you can think about it as here I add some wheels and it can go in that direction. A real capacitor usually, its distance is fixed. So here it's not fixed. I'm just letting one of them move, the other one I fix with a nail. Okay?
But shouldn't the field inside the capacitor be constant no matter the...
Yes, it's constant. But it applies, because there is a field, it applies, it's constant, you're right. So...
No matter the distance between the two...
Absolutely. Absolutely. No matter the distance, it's a constant. You're absolutely correct. But again, what I said before is, say here it's a constant. This will give you the energy density. I'll show you. Then when you squeeze this, the total energy is reduced.
Oh.
Okay, so let me do that, and if you have questions, please ask me later. Let me do this very simple exercise. So first of all, if I have one plate, then okay, one plate, this is just a reminder, then I'll have an electromagnetic, a static field on both sides of this plate, and this is given by Ohm's law. This would simply be, this is kind of sigma, and there is a 2 here. I'm not going into the details here, but this is basic. So inside here, because you have the 2 plates, but one of them with a plus and one of them is with the minus, so the total field, this 2 goes away, and this is sigma divided by epsilon 0, which is just the addition of the 2 with opposite signs. I'm not writing here the direction because I think it's obvious. Okay, z, whatever. Now, we also need to calculate things. We also need the force on this plate, right? Here there is a small thing. The force is not determined by this electric field. It is determined by the electric field created by this guy acting on this guy. That is, the electric field induced by this one doesn't act on itself to move it. Right? I wish I could pull myself and then I could go to wherever I want, but that's impossible. So the field that this guy feels is given by this this field. This is the electric field, but of course the force is related to the electric field. So what is the force? The force, that's denoted by F, is simply given by sigma times A. Sigma times A is simply the charge on this guy. Very simple. And then I need sigma 2E0. This 2 is because of this guy acting on this one. It's not this field, right? Actually, the 2 here is the main part of this calculation. Soon you'll see what I mean. And then I have it in the z direction, where I define z. This is an attracting, so the force is in this z direction. So it's a very simple expression. Then I can use basic things. For example, you start at rest, then I have the acceleration times t, but I know the force. Again, I know This is again, I'm using the V0, you start at rest. So I know the F. If I know the F, I know the A. A is acceleration. And this is simply given by F over M times T. The final kinetic energy. Okay, so you can ask, what is T max? What is T max? The T heating time. You all know this. This is the famous equation from high school, x AT squared over 2, right? So this T max, I'm just inverting it, is given by square 2D over A. And again, A is F over M. You all understand what is the heating time? This is just the opposite. Square this is T squared A divided by 2 is D. That's x equal AT squared over 2. This is the heating time. This is the time it took it to move here. And then I'm not going to go into full details because they are trivial. So I need to plug in this. So the kinetic energy is V T max T heating squared M over 2. And if you plug in the numbers, you get a trivial result, which you all know. What is this actually? This is simply F times D. And this is well known because this is just the work you do when you go against the force Fd. This is the conservation of energy, the usual conservation high school energy. So far there's nothing absolutely, nothing new. I know the F, this is F in absolute value, and I can calculate everything. So let us write the kinetic energy from this calculation. It's sigma squared A 2 epsilon 0 times D. And what is this? This is, again, I just repeat, sigma times A is the charge on one of the plate. Sigma over 2E0 is the electric field created by the other plate. Charge times electric field by the other plate. That gives you the force. Times D, the work. The work goes into the kinetic energy. Okay, so of course here there is nothing especially new. And now what is new, maybe or maybe not, is that let us do it in a different way and see that the energy, where it came from. As I mentioned, it came from here, from the vanishing of the field between the two plates. So let us do this bookkeeping. What is the energy? Now this, I'm going to remind you an equation that we already proved in this class 2, 3, or 4 weeks ago, maybe even more. And that is, we took charges and we took them from infinity and we added them. And then if you remember, we showed that if you take the electric field squared, integrate over all space, with this epsilon 0, that will give you the total energy. And we will prove it later, again, in a different way. So soon, don't worry, the math will become very complicated. So what is this energy based on that equation? Energy of electromagnetic field. This is the energy you lose. This is the energy that you had at the beginning, at this stage. Eventually, this will go to 0 and it will be transformed to this one. This is given by E squared d tau over the volume, epsilon 0 over 2. So the 2 is important here. Now here I need to use not the 1, I need to use the real electromagnetic. This is the sigma over epsilon 0. And then this is sigma squared over epsilon 0 squared from here. But I have this epsilon 0, and then I have T, and then I have here AD. And the whole issue here is that now I'm very happy because this energy is the same as this energy, and it all works. There is a balance, and there is a conservation of energy. It's not that at the end, with some velocity, it came from the vanishing of the region in space where there was some energy stored here. Energy stored here is very good because maybe we can use it for many things, and indeed we can. So now we see this concept of energy in the field itself, how it transforms to something that is measurable and understandable. But now, again, as I mentioned already, there are many different types of transformations of energies. So now we are starting to think about what are the other options, not only kinetic energy, which is boring. By the way, see this problem, in some sense it's the same as if I rotate it, and this is a kind of mass falling down in space. It's similar but different than this usual problem of a mass falling down. The reason is that here, with the two plates, the region of the electromagnetic field totally vanishes. Well, once you have one mass going down, which is a similar problem, the gravitational field is not vanishing in those type of problems. But so this is a different problem where this is squeezed. But again, all these type of equations are the same for particle falling, but you need a plate. Now, in gravitational fields, you might have similar things. If you have two gravitational fields, because what's the difference between gravitation and Coulomb field? But in a practical way, at least, this came from electromagnetic fields because you can control these fields while controlling taking two plates with infinite mass and smashing them together in a gravitational experiment is very hard, right? I mean, we don't want to do that, especially if we are in between those two huge objects. But so you can think about gravitation also in these types of things, but my point here is simple, that the concept of a field here, electromagnetic field, that contains in it energy is very deep and far beyond the example of electromagnetism. And then the first question we can ask, okay, so now, okay, this was just a motivation, and now we are going to change a bit directions, and we are going to ask, what is carrying this energy and also later momentum? And this is going to be waves. So now I want to do something else. I'm actually jumping to chapter 9. I want to show the connection of electromagnetism with light, which I guess you heard about before. So we are going to do this in matter. In matter means we have these nasty H and D and all these things. So let us see the light. And later we will relate this to concepts of energy and things like that. So we are looking at dielectric materials where the current is J equals 0. So by the way, dielectric materials, if you don't like to think about the material, also the vacuum is a dielectric material. So just free space. Then there's no magnetization and no polarization, but that is fine. We don't have but the system is linear. So this is a simplification, and it's isotropic. So I'm not thinking about a slab where different regions have different dielectric properties, something very simple and general. So in this case, just a reminder, we have this B is equal mu r mu 0 h, and d, which is the displacement vector, is er e0 e. But if you don't like h and d, and I think many people don't like them so much, just think about h and b the same up to some constant. That's also okay. So remember, h comes from the magnetization well, B is the real field. You have a magnetization field because of some dipoles. And here you have a polarization field due to some electric dipoles. So here it's magnetic dipoles, here it's electric dipoles. And this gives you the transformation. And these numbers, mu r and er, are just some numbers bigger than 1 that depend on the material that you are looking at. And epsilon 0 and mu 0 are the usual permittivities of the vacuum. Okay, so now how do we get light out of this? We first going to write the Maxwell equations that we had previous. So what are the Maxwell's equations? Let's write them here. Div D, maybe I should not write with this. I think this is better. Sorry, div E, it's the same, but in okay, div E, is this good? Is going to be equal to 0. This is because rho f is 0. There's no charges in the place we are looking at. There are no charges. This means that it doesn't mean that there are no charges totally. It just means that the electromagnetic fields are created by some source which is far away from the region that I'm looking at now. So of course something has to be creating the fields, but we are looking at the region in space where there's no currents and there's no charges, etc. I don't know which one is a good one. So usually this comes with D, but D is proportional to E, so this is the same thing here. No, this is even worse. Someone have a good pen? Okay, div B. What is div B? That is always 0. There's no monopoles. What do we have else? We have curl E is minus dB dt. This is Faraday. And what else do we have? We have curl B. What is curl B equal? You have J equals 0, so there's no ampere term, but there is the Maxwell correction term. So we have here mu r, mu 0, er, u 0, dE, dt. So this is a Maxwell ampere, but actually you have only the Maxwell term because J is 0, so these are the equations. And here I use the fact that I'm inside a linear medium, so I have here UR, ER, but in vacuum this one would be 1 and 1. So these are the basic equations. And now from these equations, Maxwell showed that the light comes out, and I'm going to show this also here. So the idea is to apply a curl Okay, let us label these equations. 1, 2, 3, 4. We are going to apply a curl. And on which equation are we going to apply a curl? We're going to apply a curl on this one. If I apply a curl and then I will play with it, I hope to get a wave equation out of this. This is the general idea. And you see, when I apply a curl here, then this one will be a curl. This will give you the time dependent. This will lead us to to kind of a wave equation. So apply a curl and then use curl to 3. Then I use curl, curl. So this is like E. This is like taking the second derivative in some sense, so we can find the following. This is just some mathematical div E minus Laplacian of E. And here we are very happy because what is dV? That is 0. So this horrible object of 2 cals gives you just the second derivative, and this reminds you, of course, of the wave equation. So what do I get? I get the Laplacian of E with a minus sign equal minus d over dt. But then now I added a cal here, so I have cal b. This comes from, this comes from 3. But what is cal b? We have it. So, and it's proportional to the derivative of E with respect to t. So this guy is proportional to the derivative of E with respect to t, this term. And that's why we have here the Laplacian, and what we will have here, the second derivative of the electric field. And that is great. That's really great, because what we get here from 4 is the wave equation, which you all know, I hope, is equal mu r, again, a number between 0 and 1, er, some property of the dielectric medium, E0, second derivative with respect to time, E. And a similar equation you can get also for B. I'm actually not going to get it, but this is the famous wave equation. And we know how to solve this wave equation. I'm not going to go into too much details, but I'm going to remind you a little bit. But what is the consequence of this? The main consequence of this is the following. You see here, I have something like velocity squared, just from the units analysis. This is 1 over a meter squared. This is 1 over time squared. So this has to be 1 over velocity squared. What is this velocity? I think you all know, so I'm sorry I cannot surprise you really. It is, what is it?
Speed of light.
Not exactly, speed of light in the material. And the speed of light in the material is given by what? In usual textbooks or
1 over square of.
Yeah, it's given by this thing, but there is a constant that we call it, usually it has a n, which comes into Snell's law. So just to summarize this, first of all, we have some electromagnetic fields E. And it's proportional to EI. Okay, this is one form of the solution of this equation. And I think you all know it. When you take the Laplacian, you'll get here this k squared outside. And then you'll have, when you take the time derivative, you'll get the w squared outside. And these k and w are related by a well-known constant, which is this speed that we were talking about. Now, what is this solution? This solution is a very special solution of the wave equation. These are called free waves. The free waves, you can take a linear combination of them, and you can add them and create all kinds of different waves. So this special solution is very special, but I think we all understand how to construct. This is also in quantum mechanics. You have an eigenvalue and an eigenvector, and you sum up many depending on the initial conditions you can propagate. So I'm going to discuss mainly these free waves, but from there you can construct many things. Now, this E is not, I'm not defining it right now. We still don't know in which direction does it go. That's one question that we have to be left open. We did choose a propagation direction here. This is a choice, kz. I could choose ky, kz, kx, whatever, but I choose one direction of propagation of k, and then I can do other things, of course, together with it. So we need to know what is this constant here exactly. And then the issue with these waves is also B will have a similar kind of free wave structure, very simple. However, the E and the B are related one to another through these equations. So It's not that you can just take some B arbitrarily of E. While this equation is a wave equation for E, and you can have a wave equation for B, these two objects have to be related one to the other. They are constrained. There's a constraint between the two. And this will define which directions can you propagate what appears here, and the similarly for B, what appears here in front. And it's not independent. The field E is not independent of the field B, even though you can write two equations. There are constraints that come from here. Okay, so let us see this. So first of all, what is the velocity? The velocity, you can see it from here. The velocity is simply 1 over UR, U0, ER, E0 square root. This is by definition, this is of course a miracle that one of the nice things about physics, that when Maxwell did this or whoever did it, he found suddenly this connection to the speed of light, so you have connections between electromagnetism and light. And this will be actually what we are going to continue, because this means that there is a connection to radiation, etc. So, and N, as I mentioned, is usually, you see the definition from here, is given by 1 over square root of UR, ER. So N is always bigger or equal 1. So the speed of the wave in matter is always less than c. In vacuum it's c. So c is 1 over u0 epsilon 0. One of the most famous relations between constants of electromagnetism and speed of light. So of course, yeah, I didn't mention W is equal, I mentioned it, but I didn't write the equation. This is the dispersion relation, and this dispersion relation is linear in K, unlike, for example, quantum mechanics, where it's K squared. So this is a very standard wave equation type of solution. And this comes from the fact that space, you see here, space and time are actually, in some sense, treated in the same way. We have the second derivative in space and the second derivative in time. There's symmetry between time and space, which is very important because of relativity, which will come later. Okay, so we have this well-known solution. Now we want to just fix these directions and understand it a bit better. Now, this field has a density of what? Of energy. But now this energy, I'm going back to my problem. Before the energy was fixed, right? It was static. The energy density, E squared, right? E squared. Of course, here you need to take the real part of this to get the field. That's the meaning of this equation, the real part of this. So the real part of this is some cosine, right? With kz of minus omega t, maybe with a phase. The square of it is the energy density of the electromagnetic field. And what does it mean? You have a point, and it's oscillating like cosine squared. So you have a point in space in this description where the energy at a given point is changing in time like crazy, not like in the first example. Because of the time dependence now, it's very different than what we had before. And then if the energy is changing in time, then what is coming in and what is going out to change it in a periodic way. Very different than usual things. So with some imagination, you already see the energy density here is very special. But to calculate it, we need this pointing vector. So we need, and to get the pointing vector, we need the directions. So let us first find the directions of these well-known fields. How do we get them? And also find B, of course. So, okay, so what do we know? Well, let's start from the beginning. We have div E equals 0. That is simply there's no charges, rho free is 0. But E, whatever the direction is, depends only on Z, right? So what does this mean? It means dz Ez. What is Ez? It's not an easy lesson. It's E, the electric field in the direction z. So this is one part of the vector. Why do I say this? Because we have also Ex and Ey, but you see the field depends only on z, so I need to only keep the rest 0, so I'm not writing them at all. So this is some additional constraint. In addition, we have Bz equals 0. This is because div B is equal to 0. Here I'm using the fact that also the B is going to propagate in this. It will also depend on the z direction. This you can show. I'm not showing it right now, but here I'm assuming that this B also depends only on z, so you get this type of an equation. So, but to look at it a bit deeper, what you really need is this equation. So let us write it explicitly. So you have rotor E. Okay, it's x, y, z, ddx, ddy, ddzz, ex, which is a function of z, ey, which is a function of z, and ez, which is a function of z. This is minus dB over dt. This is the second part of this equation. So let us look at the z component. So the z component is dx eyz minus dy dx z, and this is obviously equal to 0 because I assume that the electric field is only depending on the z direction. I assumed it here. So these derivatives with respect to x and with respect to y are 0. This is 0, but on the other hand, for this side of the equation, this is of course bd bz dt. So what we have here is not only the derivative with respect to z of bz, but also the time derivative is 0. And then in general, what we get is that bz of x and t is going to be equal to 0. It cannot be a constant independent of the field, because then it will violate, because we assume that this b is also proportional to ikz. I'm not actually proving that it cannot be a constant, but I'm going to assume that bz, if it doesn't depend on time, it doesn't depend on space, okay, then this guy is 0, this guy is 0, then everything goes away. There's no such solution. It's kind of, I think, easy to prove. So the bottom line is that the bz, which we assumed as a function of z, is 0. Okay, this doesn't solve the problem. We also, because if I put here bz equals 0, then I also get from these equations, actually from this one, I'm going to say that Ez is also equal to 0, which would satisfy this equation. There's no plus constant here. It's just this plane wave, so there's no additional function independent of z here, so from here it's immediately that this thing is. So immediately, what do we learn here? What do we learn here is the following, that if I have this plane, this is the z direction, this is the xy plane, the waves are in this plane. The z, what is z again? The direction of propagation of the wave that I assumed in the beginning. So I have a propagation in the kz, and then these are in the perpendicular plane. These type of waves are called transverse waves. So electromagnetic fields are transverse waves. You could have longitudinal waves, like in, let's say you have a pipe and you have a density, and you look at the density, there's a propagation in this direction, and then there is a small higher density, lower density, etc. It's in the direction of the propagation. I think this you studied already in your class in waves, whatever. But now we have this this equation. So now how do we continue? We have freedom of choice still, and we are going to choose now a polarization. It's a confusing word, polarization, but because we had polarization in the context of you can think why the heck I'm calling it polarization. I can give you the answer even. It's not me, but some guy. So defining the polarization means I'm going to assume now that there is this direction of the field EI kx minus omega t. Again, there is a freedom. I don't need to choose this x direction as the direction of polarization, but I can. Now, why do I call it polarization? Because this is historical name, maybe it's not a good name. The polarization is proportional to the electric magnetic field, right? So the direction of P is proportional to E, so P polarization is proportional to E, and then the direction of the polarization is X. This is how it came, but I think it's a bad name today. But this is called today, everyone will call it the polarization of this wave. So the propagation is in the Z direction, and the direction of this amplitude is in X direction. And the electric field defines the polarization direction. It's all definitions. It's not something very deep. Yeah.
You wrote twice x in the direction, x in the...
Yeah, this is a vector, a unit vector, as usual in this class. This is a unit vector in the x direction. Yes. It's not an, here is the listing. Yeah, sorry, this is z, thank you. This is z, as before. I'm not going to change this. Okay, so if this is the polarization, and I can choose other polarizations, the point is not what is the direction of this field. What is important is the direction of the magnetic field relative to this one. What is the angle between them? Because they feel it has one polarization, and this is, you can put it differently. I choose there is some direction of this field, E, and I choose the x-axis along this field. So this is just a definition. Now the question is, what happens to B? So let us do this. So I'm going to use again this one. Okay, so it's so hard. X, Y, Z, d dx, d dy, d dz, and by now, because of this is E, I know that I have here only Ex of Z. This is 0 and this is 0. And this is minus dB dt. Now, we said already, let us look at Bx, just for the fun of it. So the Bx, I need to, the point is that it's easy to show that Bx dt is equal 0. Because x dy dt, this will give you the Bx here. So this is a 0. And because the fields are proportional to t, this means that Bx is equal 0. So what I'm left with, it's not in the z direction, it's not in the x direction. Let us look at the y direction. Why is the y direction important? Because you see here d dz operating on this. So the equations I get, again, from this one is for z direction, is the following. It's dy, not the z, the direction, the y direction. Okay, okay, this you need to take care of the sign. So this one will be, the first one is multiplied by 1, this is minus 1, and then this is in this direction, that's another minus 1. So it's minus 1 times minus 1, it's going to be a plus. So I have d over dz, exz, minus, if I didn't make a mistake, db, dy, dt. What is this derivative here? It's easy. This is a component of the field, so there's no vector here. From here I get the following. I get ik E0. Just taking the derivative here, I just get ik down here. And if I assume a plane wave like this one, which solves the equation, this is what we are showing now. So it's a solution, and assuming a uniqueness, etc. When I will take the derivative, assuming this type of frequency dependence, what will I get? From the derivative, you have a minus and an I, so you'll get minus, you get here B0 I omega. Yeah, the minus and then another minus, and then the I omega is here. No. Okay, so I didn't mention this. I assume that B is proportional to some B0 EIKZ minus omega t. So there is a wave in the B direction. I don't know, at this moment, I don't know what is its B0. There is also an E0. In principle, these two are independent. But the whole point is now to show that they depend one on the other. Okay? That's the idea here of this, exercise. So, but you see here that the relation between E0 and B0 is given by the division of W by K, or K by W, and what is that? That is the speed. That's the speed that we had before. This was in the dispersion relation that we had before. So what we see is the following. So to summarize, summary. First of all, E is perpendicular to B. So if this one was in X, this one will be in Y. It means that B of Z is some B0 EIKZ minus omega t, and here I have a Y. Yeah, this comes from here. You see, this by, this is the by. This was the only component left in this equation. So we have bz is in the y direction. The propagation of the wave is in the z direction. The electric field is in the x direction. But b0 and e0 are related by this relation. So this is the next point. The ratio of b0 and e0 is the following: e0 divided by b0, it's given by this one, is equal to omega divided by k, which is v, which is c over n. In general, it's c over n. This is the summary. And now we can plot it like this. So you see, let's say n is equal 1, you see that the E0 in these divided by B is simply the C, which in general is thought as a big number, but of course the units are different. So this is the way. So here I want to plot, this axis is the Z axis, this axis is X, Y. So this is just right hand notation, X, Y is Z. So this field is what? that's the electric field, because it's in x direction, like here. What am I plotting? I'm plotting here what is E, the real of E, that's the real field, is proportional to, let's say, some cosine in general, E0 cosine omega t minus kz, sorry, kz minus omega t. And in principle, you can add a phase. I didn't add up to now a phase, but you can add one. It doesn't have to start at 0 or whatever. Then the magnetic field is in this plane. I plotted it slightly smaller just to emphasize that it is divided by this C. And I hope you understand it goes into the blackboard. And this one is E, and this one is B. Both E and B are changing, and that's why also both the energy at the point is changing, the energy density is changing. And now we have these fields. Later we can calculate what exactly is the change of energy. So now, what is the time? Okay, so now let us go for a 10 minutes break. And after this break, we will calculate the energy in general, not only for these waves, but in full generality, showing how the electric and magnetic fields, they change in time, and then they create locally energy, and something is flowing out, which is related to the Poynting vector. But now we have the waves, so we will be able later to calculate this energy, at least in one example. Okay, so now we want to understand a bit deeper the flow of energy, the conservation of energy, and to relate between the energy conservation and the Poynting vector, which is going to be a very important quantity. It's not only important for energy conservation, it's also important for momentum transfer, and we're going to discuss it. So I'll start by some reminder and some thoughts. So we want to have the energy of a system and we'll do it, first let us remind what we did already a few weeks ago. We said the following in a very simple way. We have a charge system. This was all in electrostatics. And now we're going to use time-dependent fields. Then we said this is our configuration of charges. We're going to bring one charge from infinity to put it here. That will cost you no energy because it's not working against anything. Then you bring, let's say, this charge. It's working against the field of the first one. You bring this one, and then you bring that one. And then we could calculate what is the total energy. And it's important to understand what is the meaning of energy here. The energy composed into this system, the energy that you need to invest in order to create this system of charges. And this was given by this view, electromagnetism, electric field, let's say in a static case, was E0/2. I used this previously in the previous lesson. Integral over the whole volume. Now there is also magnetic field, which I didn't prove, because I'm going to prove it now in more generality. But this, if you are interested, you can read it in Griffiths. He does it by bringing not point charges, but by bringing kind of loops that have some inductance that create interaction, and you can also prove this in statics. We want to prove the total energy is going to be the sum of this energy plus this energy. This is going to be the message. We're going to prove it, but we're going to prove it through balances. What do I mean by balances? So we have a system this will be the message. We have a system in some volume. So this is a system. And then there will be some energy change. What is this energy change? For example, creating heat. This is the creation of heat is what we're going to use here. So there are some currents here. And because there are currents, you are creating heat. This is equal in a change of the electromagnetic fields, change of the energy What do I mean by the change of the electromagnetic? The electromagnetic fields, this one and this one can change, and you can transfer from this energy, let's say, to the creation of heat. That is what it means. But in addition, there will be a term of leakage. So not only energy moves from one form of energy to another in this system, you can also have leakage out of a system. What does it mean? I'm looking, this system is part of the whole universe, and some energy can flow out or come in. So this will be the total balance. You don't only transfer energy, energy can leave through the surface of this thing. And this will be the total balance of energy. I mean, this, in my opinion, makes sense, this thing. But now we need to transfer this idea into some words. This one will be related to the vector pointing. This one is related to these two guys. And this guy, for example, if it's going to be heat, it's going to be related to Joule's law. Joule's law, maybe you heard about it, but I'll remind you. So this is what we're going to do now. I mentioned already in previous class. Here I'm following the idea that you are looking at a system, electromagnetic fields in a medium. So I'm using E, B, D, and P. Griffiths does exactly the same, but he does it in vacuum. I'm using J free, he's using J. But I mentioned already that you can map the two problems, but just by, in fact, my problem is slightly more involved. I like this in field because the energy loss is very clear. The energy loss is due to heating. You have some currents and then you are heating, so the energy loss becomes very clear, so I use it in material, while Griffiths does not. But again, you should read both. So to do this, we want to write down on the side, as usual, the basic equations, which are Maxwell's equations. I'm going to use linear material, so it's not the most general thing. So the first equation is div D, again given by the E and the polarization field, is rho free. So unlike the previous class, now there is some charge density rho free somewhere in space. This is of course Gauss law. We have div B, that is equal 0. We have KLE, that is dB dt, that is Faraday. And then we have KLH, this is equal J free plus dd dt. And as usual, D and H are related to E and B with the magnetization. So again, this is Gauss, this is no magnetic charges, this is Faraday. Now I do have currents, not like previous lesson, and I use D, so D is related linearly to E as usual. Now I have J free. J free is the free charge current. Remember that in this problem you also have other currents related to dipoles and things like that, right? But what we care about is, I'm going to use only this GF. So there's a fundamental difference between the different currents, and this is what makes this problem slightly subtle. I am assuming that the Joule heating of the system is caused by this current, JF, and not by, let's say, loops of currents created that creates the magnetization. Why? I'm assuming here that, you know, let's say the system has some spin, and that is intrinsic, it's not a dissipative force. So the dissipation comes only from GF through Joule. This is an, it's not exactly an assumption, it's just I'm going to use that heat as the thing that is, this thing as the thing that creates the heat in the system to make this balance of equations. So,
can I ask a question?
yes.
I understand the assumption, but more general question. Even though that spin is intrinsic property, some fluctuation in the spin can cause dissipation, right?
Not in the way I'm looking at right now. The spin is intrinsic to the Hamiltonian,
Okay.
and it's just rotating and not.
If it's fluctuate,
Fluctuates. What do you mean fluctuate? Thermally fluctuate?
let's say so. Sure. Not necessarily, but
Yeah. So in principle, yeah, you could add these terms to some heating, but I'm not going to do that here. But you're right. But that's the difference. That's the difference between. Again, Griffiths just avoids all this completely by using the J, but I want to use the J free, and I assume that the heating comes only from the electrons moving in space. But the equations I'm going to show you are proven in full generality. So. Yeah, but the interpretation, what is heat, is a bit more subtle. Yeah, but it's an assumption. This is exactly what I said. So I'm going to use the following. These are just mathematical equations. You'll soon see why I need them. Let's call this. This is, again, a derivative of multiplication of functions, more or less. So this is h cal E minus E cal H, and div some function V, this is just an arbitrary function, D is V div D plus D grad V. All these type of equations are chapter 1 in Griffiths. I'm just going to use it, hopefully not abuse them. Okay, so now I want to calculate, again, I said before there are magnetic contributions to the energy, electric field contributions, and heat. So let us now calculate what is the heat. So there is a change, this is a small microscopical change in work. This is given by, as usual, FDL, some force acting on what? On the free charges and not on the other things in the system. This is equal to rho, I'm going to write it, rho d tau. What is rho d tau? This is the rho free actually. This is the charge density times volume. This is simply delta Q, the small charge that on which the force is exerting. What is the force coming from? It's coming from, of course, as usual, from E and B. And this is simply the Lorentz law. E plus V cross B. Dot dl. Now, this guy is rho d tau. So I use here the definition of force from high school. This is all very, I think, very clear. Charge times E gives the electric force on this volume, and here is the magnetic force.
This rho is rho free?
Yeah.
Thank you.
Everything is rho free. Then here I have, okay, let's write it, E plus V cross B. And I'm going to write dl as V dt. So this is a small displacement of this group of charges. It's a continuum description. And then dl is proportional to the V. And the point here is that V cross B dot V, this gives you 0. And this statement was already in the class. I said it already last time. The magnetic field doesn't do work. So there is a breaking of symmetry here. The magnetic field doesn't do work, but the magnetic field does contain energy inside. It's not the same thing, but this is just the work that you are doing on the material particles. So what is this? Now I'm using one more thing, and that is, what is V times rho F? That is the J free. That is by definition the density of the free particles, and then you have here JF multiplied by E d tau dt. So again, d tau is an element volume, it's somewhere in space. This is my d tau. dt, I'm looking at the work that comes from the fact that it operates for some finite time. If dt goes strongly to zero, there's no work because you didn't have time to dissipate. And the most important part of this equation is Jf times E. What is the name of this equation? You saw it before a million times, but in a different disguise. This is Joule heating. In high school, it's also taught. This is the same as high school. I mean, not exactly the same. What is the... in high school, what do they teach you? You know this famous equation for power? I times V or I squared times R, whatever. It's exactly the same because J itself is proportional to E. And then you get V. So this is like the voltomes, this is like the I. J is proportional to I, J is proportional to V. So you see, it's exactly the same, but it is also very different because this equation is local. It's in some space and point in time. X, V, these functions depend on the position where you are, and it can change in time. While just the usual high school type of calculation of the power is macroscopic, it's V times I, and that is for the whole system. So the point is that the work here, the delta work here and the delta work here can be very different if the J and the E are different in different locations. So this is a much better equation in some sense, but it is related to what you know already. It's not totally new, but it is a little bit new. Or maybe it's not new at all, I don't know. So what is the, so here I'm using the definition of J. This is rho times V. So now I don't want the local work done at some position, I want the total work. So this W here is small, but now I'm going to use big W, which is for the whole system or the whole volume that you have here. And what do I need to do? I need to integrate over the volume over space. And this dt I take to the other side, dw dt, and I integrate over space. So what is this eventually? This is eventually is going to be integral over the volume E jf d tau. This is Joule's law for the total work. That is what is this work? This is only the energy lost to dissipation. Dissipation to Joule heating, because it's related to J and to E. It's not related now to the directing fields. Now we have these, and what is the idea? And this is done in many these type of exercises. I have this EJF, but then I think for a minute, wait. I don't want to write it in terms of a current times electric field, even though this equation, of course, is fine. Let's say I don't know the current, but I know the electric fields. So what I'm going to do is, I'm going to use this equation, from the Maxwell equation, that I'll have GF, and then I can plug it in, and then I'll have H and D with the curl and the DDT, and I'll just take it here and replace this GF. Then I'll massage this equation, and then I will manage to get rid of the current. If I get rid of the current, still, this is the definition, this still holds. I'll have your expressions that are similar to this E squared and B squared and other terms. That's what I'm going to do now. It's clear? That's the general idea. To do this is to get rid of the current, which sometimes is totally unknown. it depends also on the conductivity of the matter. So let us do this. So the total work is given by following the integral over the volume, and I want to write it like this. E, I'm using this one. Let's write it here. E, how did I get the integral? You can ask me. You have a question? I went from local dissipation. This is small. And this is what is done in this box to what is done in a whole system. I need to integrate over the whole system. Okay, so I have this E from here, and then I use this equation. Then I multiply this by KLH. This is this term. And then I need to put it on the other hand. I have here E dd dt. Over the volume, that is this d tau. So now I use, let's call this one Aleph. So you see I have here E times KLH. This is this one. If I put it on the other side, and then I have these two terms that I have to take care. This one starts to remind you something that you know. What is this eventually going to give you? E cross H? The Boktek pointing, and that's the thing that is going to leave. And notice that this comes with the div. So already here you see more or less where I'm going to. So this is the volume. Let us do it carefully. Then I have here H, how do I want to do it? H curl E. This is this one. Minus div E cross H minus E dd dt. This is a pretty disgusting because it's very unsymmetrical. So we need to continue playing with this. What is KLE? KLE from Faraday, I know it's minus dB dt. And that is kind of nice because here I have something time derivative. Now I can replace this KL with a time derivative object. So let's do this volume. Minus H dB dt, that is Faraday. Let's put them together because they starting looking similar. dd dt minus div E cross H. Now we can pause for a second. Let's say we are in vacuum. What is H? H is B. And then you see here immediately you get the B squared here. You get the E times D is also E. And that's what I already said before. And in fact, we proved already this time. But now it's very different because now it depends on time and space. So, I mean, before it also depends on time. But now we have also the magnetic term. And we have this term which I'm going to call boundary term. Now, I didn't use up to now linear material. But let us use linear material. So in a linear material, I think we don't need this.
Can I ask a question about the process? When we...
One second, let me finish the process because we are nearly at the end of it, and then you can ask. Let us look at E, for example, d dt. I want to claim, it's very easy to claim actually, because D in a linear material is proportional to E. And then I can write this simply as 1/2 E d dt. So again, d is proportional to it times some constant. I can take the constant outside. I add here this half. This is the half that was before already. Now you see where it comes from. This is e squared, so when I take the derivative, I'll get the same thing. And I can do the same for the second term, which is this term with h and b. Doing so, I get the final result, which is the following. D big W, which again originally came from the work done, dissipation towards heat through Joule's law. That is the change. That is given by d dt, integral over the volume, half E dot d plus b dot h d tau. Now I use one more thing. Here I have the div, so I use the divergence theorem. Instead of integrating volume over div, I just integrate over the surface. And this one is given by E cross H, dA of the surface. This is the surface of the body. And when you think about it, the body can be anything. It doesn't need to be the body of the real body of the system. It can be anything you want. So this is exactly what I drew before. The change of energy due to the heating. This is the power in units of watt, is related to the change due to the electric fields and the thing that flows out of the system, which is this thing, which is the vector, the pointing vector E cross S. So this is exactly what I showed you previously, but now I made it into some equation. Usually, I mean, in vacuum, this D will be E, and then you'll have E squared and B squared here. And otherwise, what is D in a linear material? It's proportional to E, and it's proportional also to the polarization. So we have here a term, E times P, which also makes some sense when you think about it, because E times P is the energy of the dipole inside the magnetic field, the microscopical dipole. So we added here, the new thing compared to what we had before is that this D here replaces the E. Now again, in a linear material, this is actually E squared, right? Because D is proportional to E, and you have these ER inside here, so this is simply ER multiplied by some constant. So there's no big difference in this equation, in this part of the equation, from a vacuum. Yeah, what is the question?
When we got d omega equal to EJF d tau dt. Before.
Here?
Before the integral, we have d omega equal.
Yeah, here, right?
Yes. D omega equal EJF d tau dt, and then we integrate the right side, and what about the left side? We don't.
No, this is the big W.
Ah, okay.
This is small w. So if you want, the big W, I didn't write it, but it's the integral of dW over the whole system. This is the total energy, and this is a local energy dissipated locally.
המשוואה שכתבנו פה זה רק בחומרים לינאריים?
כן. There is a, yeah.
כן, הזהות שכתבת למעלה פה היא רק באמת כש-D פרופורציונלי ל-E ואין וקטור פולריזציה.
This equation.
המשוואה הזאת, כן.
Yeah, this is only for linear material.
בעצם זה תמיד יהיה E בריבוע פה, באינטגרל הזה.
Why? I mean, you see here H, B, E, D. Let's assume that D is not linear in E. D is E to the, okay, in small e, let's say it's linear in E. But then there's a correction term, E to the power 22 or E to the power 2, 3, whatever, like a series expansion of D with E. Then you will have your terms that are E and then higher order in E, etc., etc. And generally,
כן, אבל הזהות שכתבת פה לא נכונה.
yeah, so here exactly, this is what I said, that here assume a linear medium. If the system is not a linear system, then you need to this is the correct equation. I cannot take the dt outside. It's not a bad equation, but I cannot take the dt out here. Which is nice to take it out here because this is the energy, right? And you take the derivative of the total energy, but in this case it's inside here, so it's a bit more complicated. So this is again only linear material. There is a, if you are very interested, you can go to Jackson. This is the equation for nonlinear material in general. But it's not so elegant. Yeah.
Can you please explain the second term again in the equation, in the final equation?
What is this is the final equation.
Yes, the second term, the E cross H. No, where are you pointing?
Here?
Yes, the surface.
So look what you have here. I mentioned it briefly. You have the integral over volume of the material, div E dot H, over d tau, over the whole volume. Div, the way I remember, whenever you have an integral over a derivative of something, you know that you are doing something stupid because the integral over the derivative of something should be, you should be able to solve this. In one dimension you can always solve it. But this is simply the divergence theorem where you take the integral over the volume over d and replace this integral over the volume with an integration over the surface. So here we have only the integral over the surface. So I did it.
But what is the physical meaning?
Okay, so what is the physical meaning? I mean, okay, we will discuss this more and more. But going back to my analogy that we are starting to see this, here we have the vector pointing, I'll soon define it, in medium. This describes some process which is on the surface. This you agree. This describes what's going inside the volume. So this is interpreted as the energy that is leaving the system. Taking again this example that I use maybe too often. You have students in the class, some of them leave. That's one way of losing energy through the surface. This is through the vector pointing. And another mechanism is by changing the energy of the fields inside the room. Hope you don't fall asleep. And this is done here. And all this is balanced by what is you transfer to, which is the heat that you create. In more generality, it doesn't need to be heat. Let's say you have in a vacuum, it can go to kinetic energy. It doesn't kinetic energy in the usual meaning, not of course heat is also kinetic energy. That was the example that we started in roughly an hour and a half ago, where we transferred kinetic energy into electric energy, which was only this. It was actually there was no this term, there was no B, there was only E squared, there was vacuum, and we transferred it into kinetic energy. So the difficult part here, in my opinion, is beyond the electromagnetism, is that you are transferring energy between different things. Heat, electromagnetism, flow outside from the boundaries, creation of energy inside, to mechanical energy, whatever. You need to know how to juggle between these two, because this is not so surprising, because when you transform energy, you can transform energy in many different ways. Now, this flow of energy from the surface, which is really the beautiful thing here, is caused here because the fields create energy density. Once you have that, usually what do you think about energy? Let's say in high school, I love high school, all the real physics is there. You have a particle. It has a kinetic energy and it has a potential energy. Here we are saying something different. The fields themselves in space contain inside some energy, and they can change. And this comes here, and because the fields themselves can contain, you can have the leakage of energy outside of, of a volume, because something is going out. You can make an analogy to, let's say you have particles in some region, and there are some velocities. If some of them will leave, you will reduce the energy, right? So you care about, because of kinetic energy, for example. So it makes a lot of sense, this thing, but this formalizes everything in a very elegant way. Okay, now we need to play with this equation and see what it means. So we now continue with, we now define this as the pointing vector. There are two, usually in the books there are two pointing vectors. And there's one vector pointing which is given by P. P for pointing, but P is also polarization, so it's very annoying. And that is when you work in medium. So one definition is I'm going to write it like this, pointing. Not to be confused with polarization is E cross H. Again, this is just a definition. This is what you have here. What happens in vacuum? Now, in vacuum I'm doing a leap, because in vacuum there is no, we are not considering here, what do I mean vacuum first of all? I mean, you may have particles, but you are not creating heat, but you may change, let's say, kinetic energy. So you are still changing the energy of the system. For example, reducing speeds and things like that, which is similar. So in vacuum, it's the same equation like before. This is in Griffiths, dW minus d over dt, the volume. Now there's no electric media, so it's E0 E squared plus half B squared over U0 d tau minus 1 over U0. This comes from the definition of H and B. I'm not going here into the detail, so I'm just changing this H to a B, and also this D to an E, and etc. So H is actually B divided by U0 when there's no magnetization. And here I have on the surface E cross B dot dA. So this is also a famous equation. It's the same equation. Just remove the vacuum. And then you need to think carefully, what is the W dt? And if there's no heat created, fine. What happens if there's no heat created and there's no change in energy? This is zero. It could be zero. So this is subtle. So if you don't identify a loss of energy, then you have only these two terms. This one is zero. You need to understand what you're doing. Or if the energy is transferred to something else, like kinetic energy, you have this term. So it's a subtle equation depending on the context that you're looking at. And then in this case, we have S. This is also vector pointing. It's this thing. It's E cross B divided by U0. It's also vector pointing in vacuum.
pointing in Y.
But I like to point. You're right. This is because my text is in Hebrew. Okay, so you can rewrite this in a different way. Hope you will follow. So I can, let's say the change of energy here is done due to some change in kinetic energy of some particles. So what I'm going to do, I'm going to put this term on the other side. And so we want to formulate, it's the same thing, formulate a continuity equation. Why do I formulate the continuity equation? Because what we see here and here is something leaving the surface, and there should be also conservation of the total energy, not specific energy of electromagnetic fields. We already saw that the electromagnetic field, you add to them something, some change, heat, whatever. So we are going to use some, this is not a material, this is some general volume in space. And then we have here some vector pointing. I'm using the free space. And here I have some dA. This is this one here, SdA. And now I'm going in reverse in the class. What is this integral? It was an integral over the volume, right? So I'm going back now. I hope you can do that. And then I have div of S, right? I have div of S. Here I have all this junk. And then here I have the derivative of the time, so I'm going to put this on the other side of this one. And then I'm going to get rid of the integral, because the volume is arbitrary. And I'm going to be left with the density of the energy due to the electromagnetic field. And the density that is changing, the density of the energy that is changing, let's say heat or mechanical energy in general, by putting this on this side, and this will be equal to div of this thing. So I hope you can all see, or not, you can read this. So I'm going to write it as E mechanical plus U electromagnetic. By putting on the other hand, this is equal to minus ds. This is the continuity equation, which is exactly the same as before. But now, what am I using? What is different? I gained something, but maybe made you more, you don't understand this equation, which is fine. What did I gain? I don't need to do these volume integrals. This is a good thing. So what are these things? These are energies per unit volume of the electromagnetic fields and of the mechanical motion. Maybe some other chemical, whatever energy you have in the system. And what does this say? The total change of the density of the energy is equal to this div. This is same as the usual continuity equation. So something is flowing in with this S and something is flowing out, and the div of S will give you the net balance. Why? If S comes in, S comes out is the same, then this will be zero, and then you will have conservation of energy. So this describes the loss terms due to flowing out of this volume here, whatever that volume is. But now what I did is actually take this volume and made it a very local rule. Made it a very local law, just to be sure that you understand what is the electromagnetic density. So at each point in space and time, I have some density of electromagnetic field, which can go into kinetic energy, for example, or whatever, and that is simply again, this is definition. So each point in space has some density of energy given by these expressions, and then you can transfer it to different places. This energy density, there is a flow out and flow in, which is related to this S. So let us see now. Okay, let us see. Now we can plug in. What I'm going to do now is I'm going to use an example, and the example would be the free waves that we derived before. So I know what is E, I know what is B, and I calculate S, and then we can estimate these things for free waves that are time and space dependent.
אני אפשר לשאול שאלה?
כן.
פה כאילו יש B בריבוע, ושם יש ערך מוחלט של B בריבוע.
Yeah, but this is the same. Maybe I'm a bit sloppy. E dot E. This is what I mean by B. It's the same. So let us check and see what this all means. So, so as before, we have, this is the z direction, this is the x direction, this is the y. We have these strange fields that we already solved with the Maxwell equation, and this is the magnetic field. Bad drawing, but okay. So what is, first of all, what is the energy density at a point? It's given by this equation. So let's just copy this, E squared E0 plus B squared U0. Here I'm in free space, so there is no ER and nothing of the sort. But what did we learn before? There was this amplitude of the field is given by E0 squared over C squared. This is U0 epsilon 0 E0 squared. Remember, what is this 0? This was the amplitude of the magnetic field. It's not a vector. And this is the amplitude of the electric field. And the amplitude of the magnetic field we show was damped by the C factor, one compared to the other. So this is what we had before. And then if I plug it into these equations, what do I get? I get this U. I'll just copy it from here. Is simply equal. So the point here is that this B and this E give you the same amount of contributions, more or less. This is E0 squared, cosine squared, KZ minus omega t. There could be some phase. So this is the thing I'm using here. So here I'm using the fact that B and E are depending on one another, and to get this energy density, this has the right units because this has the right units, and there are no two terms, but of course it's a very strange energy density because it depends on time in principle. It is oscillating, and if it's oscillating, then the derivative of it is something, and that means S has to be something. It's not 0, which means that this is one of the reasons that we had to have this S is so important to see what is going in and what is going out to compensate it. This equation is also very strange from point of view of quantum mechanics, because you see that the energy is related to E0 squared, the size of the field, and not to the frequency of the field. This later in quantum mechanics, this equation was one of the shocks when quantum mechanics came, that the energy is proportional also to the frequency in some sense, the photoelectric effect. But we are not talking about this here, we're not talking about quantum at all, but it is a kind of strange. Now let us calculate the S. It's also simple, because we calculated already the S is 1 over U0 E cross B. We calculated E and we calculated B, and remember that E was in the X direction, Y was in the Y direction. It's in this figure. So S will be in the Z direction. So S is going in the same way as the propagation of the wave. So it's easy to calculate it. Let us do this. Just plug in this one times E0 E cross B. This is just a way to write it. This is equal to the following: C squared epsilon 0 okay, E0 times X cross, the other one was E0 divided by C, that is the magnetic field, cross Y, so X cross Y, and here I have cosine, because both of them have the same dependence, cosine kz minus omega t plus delta. So S, after you do this calculation, it's easy, is given by this C epsilon 0 E0, the size of the electric field, whatever it is, cosine squared kz minus omega t plus delta.
We can just get the cosine outside of the cross?
Yeah, because these are the scalar, this is the direction x and y. I'm multiplying it, but all the rest are scalars, I'm just multiplying them.
Okay.
But then you immediately see by comparing these two terms that S, you can write it in a more easy way, C the energy density times Z. And then it's very easy to prove the not prove. We know that the continuity equation works, but we can do this du dt. What is the point? So my point here is the following. There is no mechanical energy here, right? Because there's no particles here, so I can get rid of this one here. There's only electromagnetic fields, because this is what I have put into my problem. So the derivative of the electric magnetic density should give you this minus ds. In this simple example, we calculated them, and then you see they are proportional. And then taking the spatial derivative of s in the z direction is going to be exactly the same as taking the time derivative. This will come from what? From the dispersion relation between w and q. It's the same thing, and then you can easily, I leave it for you for an exercise to show that this is ds dz as expected. I write it like this. It's the s in the z direction, so which is the same as this one. Why it's only in the z direction? Because the s depends only on z, and then the only derivatives that are left here are with respect to z, not with respect to x and y. So I can easily show this, and this is a continuity equation. This div is much simpler here. I put it also on the other side. The change of the density of the energy in time is related to the things that are flowing out, but they're a spatial extent, the derivative in space of them. So this is exactly what is written here. And at least in this problem it makes sense. You have some, there's no material here. There's nothing, there's no heat created here, but the energy, local energy is changing due to something that is leaving. What is this something? That is this is the Poynting vector. But something is leaving, and in the next lesson we will learn what is this S. So this S is also flux of momentum. I'm not going to prove it this lesson, because to prove it I need the stress tensors. So instead of that, I'm going to, in the time remaining, discuss a little bit. Okay, so before doing that, usually when you look at S, you see this is changing in time in a crazy way. So in many cases what we actually do is look in experiments at S average. This is an average over some cycles. This comes from physics in principle, and it's not mandatory. What does it mean? The frequencies, let's say you are looking at light, visible light. The frequencies are extremely high, let's say 10 to the 10, 10 to the 15 hertz. This field change, this oscillation in this thing is so fast, then in usual measurement device, in fact I think in all of them, you cannot measure at one time the energy density and then, so what you do is you average over time. You average time this cosine, okay, let's average S in absolute value, that gives you CU average. That will be, what is the average of this function? No matter what is Z, it's half. Because it's a cosine function that goes between 0 and 1, the average of this is half. So another type of equation you'll see many times is C epsilon 0 E0 squared divided by half. And again, this is independent of the frequency. It just means the following, that the energy density increases quadratically with the energy, and then S, which is related to the flow, is related to the velocity of light coming out. And again, this is what people usually call intensity, or what classical people expect from an intensity to increase with the amplitude of the field and not with the frequency of the field. So, so now in the time remaining, I'm going to move into something slightly different. I'm going to discuss what we will prove next lesson. I'm going to discuss momentum, and then I'll go into some paradox of momentum, which is relatively, it's not so mathematical. It was some idea that Einstein had that is related to special relativity. And this, I hope, will convince you to read deeply on the stress tensor, which gives you the forces. And these forces are related to momentum, because this is from Newton's law, this is obvious. So, in addition to the density of the electric field, there is another density of momentum. So what do I mean by that is that if I have, for example, a sail, a mirror, and I have some light coming on it, in principle this sail will move, and you can think about it as some particles coming and hitting it, transferring momentum. This momentum is related to this S. Again, we will prove it next lesson when we discuss the stress tensor, but for now we are just going to start playing with this. And the claim is, and you will read it in Griffiths, so this is momentum per unit volume. So again, I have some space, and in this case, I look here in the electromagnetic fields, and I claim, I'm not proving, that in this point in space, you look at some momentum, and I'll explain this in an example, and you'll have some momentum per unit volume, and this momentum can change or move around, and it can hit a mirror, and it can create, but this is a momentum that is special in the sense that this is a momentum created by the fields. So it's a new concept for you, which I will just use here, and we claim that this is equal to U0 epsilon 0 times S. So this guy, U0 epsilon 0, is 1 over C squared. So I want to use this, or start thinking about this, how Einstein thought about this, because I don't want to have too many complicated stress tensors and things like this. It's a bit too late for that. Let us think about these things. Einstein was thinking, not solving complicated math most of the time. And then when he started to solve complicated math, he got stuck. But eventually he managed. It's not that his math was bad, but he was mainly thinking about things. So, I want to think about the following question. Does anyone have a good pen?
Yes.
So, this is a kind of a train that lives on a frictionless surface, so in principle it can move. And the question that we will soon solve is the following. I have a person here, and it has a flashlight, and he turns the flashlight on. Now, because he's turning this on, he's sending something like bullets, if you want. In Israel, everything has to be bullets or whatever. And these things are moving here, and they will impinge the wall. What will happen here? The basic question is, what will happen in principle? What will happen here in principle is the whole system has total momentum 0 at the beginning. So if you shoot something in this direction, then this cart has to move in the other direction. Just conservation of total momentum. And we believe in conservation of total momentum because this is something deep related to homogeneity of space. I mean, we can violate many things, but we don't want to violate that. To understand this, let us start from the classical description where these, instead of light, we are just shooting some bullets. It's a cowboy shooting some bullets. So we will define M as the total mass, including bullets, and M is the mass of the bullets, maybe one bullet. Now, one way to look at it, it's not the only way, is that the center of mass of this system cannot move because the total force on the total system is 0, so the center of mass of this system cannot move. And we can calculate the center, we can calculate this. There is a subtle point. When exactly do we want to calculate? We want to calculate it when this is L, this is the size, you can say the size of this object. Why? Because let's say in a real experiment, the bullet will leave and here it will be stuck eventually in the wall. And just before that, there was, it went backwards. And then we stopped the experiment just before this L. So you don't really need this barrier here. You just say, let us stop the experiment when this bullet reaches this thing here, L. And then the center of mass is going to be 0. So this center of mass is delta x of the train, m minus m plus ml divided by m. This is where the bullet eventually lands, m times l. This is this contribution. And we are going to assume all along that m is much, much smaller than m. This is delta x train is, I can put it on the other side because of the minus sign here, is this small m is negligible here. So this is 1. This is equal to ml over m. Why this is important? Because this is one way to look at things. But we can also do this in the classical world, it's very easy to do this. In a second way, and that is conservation of momentum. We have here some bullet that is going in this direction, and then this guy is getting momentum in the other direction because the total momentum is Save, and you can get the same result. Let's do it because it's easy. So we have m times u is m times v. U is the train. V is the bullet. The mass, this is not exact, but this is nearly the mass of the whole train. Neglecting the small mass like I did here, I neglected some small mass. So U train is mv divided by m. And then delta x is mmv L dot over v. What is this, L over v? That is simply the time that took the bullet to reach L, because it has a velocity v, and the nice thing here, this is cancelled. Then delta x train is m over m times L. Okay? And if L is very big, what will happen? The bullet is going in this direction, and then you have a lot of time to move in the other direction before it hits the wall. So if L goes to infinity, the train will go in the opposite direction till infinity in principle, because we don't stop until we reach this L. Okay, great. Now, in Einstein's head, with this equation, just using it, let us do the same, but with electromagnetic ideas. By the way, this is not exact. This is Einstein. He can do whatever he wants. Not really. We can later prove this. It's just a way to think about things. I'm not really solving exactly mathematics. I'm just thinking. And later we can solve not this problem, but other problems. So we have this density of the electromagnetic field that we will prove in this next class, but let us assume that this is valid. So now we want to think about what is this momentum? This is momentum per unit volume. So it's a property, local property of the space. What do we need? We need the total momentum. The total momentum that is created by the light. So we have this guy with a flashlight. This is a flashlight, not bullet, but it goes also in this direction. And then my claim is that what we're going to do is we're going to calculate momentum here. This is the momentum in this thing. When the light first hits the wall, we stop it, like the bullet got stopped. But of course you're turning on the light, and there is a lot of density here of momentum. Let us calculate this momentum and see what happens. How will we calculate it? We have this L. We need to say something about the width, but this will vanish. This will be the magic, if you want to say. So this is size L, like before, and here I have some volume, which is determined by the lamp that you emitted, some volume A, and now it looks pretty bad. So what is this delta X of the train? Let us look at it like bookkeeping. We have the momentum per unit volume. This is our equation. We know that, or we hope we know that, times the volume. What is this? This is the total momentum. We need to divide it by something to get velocity. What do we divide it by? By the mass. And we need to multiply it by time. So this is V times T. It's not high school, this is kindergarten. So this is simply V times T. Okay. Now, what am I going to do? So I need to have here the following. So I have here S divided by C squared. This is this one. I have here the volume. I have here T, and I have here the mass. S is the S is due to the lamp. It depends on many things, like the frequency of the light and all kinds of things. We're actually not calculating S. So again, this is a SAT L over M C squared. Okay. So now we are practically done. Okay, now comes a jump, Einstein's type of jump that you can accept or you don't want to accept. What does Einstein do here? He says, I want to believe in this equation. The center of mass motion has to be obeyed. We are not going to violate it in any way. And I'm going to introduce some effective mass, which will replace this mass, m effective. So I'm going to say that this is m effective times L divided by m. And I'm going to think, what is this m effective? So you see here, this L goes away, this L goes away, this m goes away, this m goes away. But what is S times A times T? Can anyone?
The energy?
It's the energy, exactly. This from before. S is the energy per unit time, per unit surface that is going through a surface. So all this guy, Einstein, this we know from the previous, this is the energy of the light. So what we have here is the following, that I just multiply this and then I get E equal m effective, you see here C squared. This is very confusing, right? But Einstein likes to confuse it because this is the real way physics is done. Because now the question is, what is m effective? What did they do here at all? Because it's very strange, because the light doesn't have a mass. So what is this thing? So Einstein says the following. It's just the beginning of a revolution. Don't think this is a real. What is this? What will happen here? In principle, I'll say it in a kind of dramatic way. If you take this light, in principle, it hits the wall, it can transfer from energy, which is the energy of the light, to a mass. But to do this transformation of energy, you need the wall, and then you will increase the mass of the wall by this size. So eventually this mass can go in principle to the train. You will increase the mass of the train in order to save this one. And this means that the energy can change from kind of electromagnetic energy to a mass that will go in the train. So if I take a train and if I heat it, in principle, I can increase its mass. If I cool it, I can decrease its mass. This is what Einstein is saying. And he got this famous equation like this. This is the historical root that he got this equation. You don't learn it like this, I think. Did you learn it like this sometime?
No.
You learn it in a different way. You learn it from special relativity, which deals with mechanics. But this is his famous, he derived it in two ways. I mean, this was just a starting point. He was thinking about these equations, and he was thinking about these trains, and he got this thing, and he could not really understand what is this M effective here. He was thinking about it for many days and many weeks, and eventually it sunk into him, yeah, mass is really, you can transform energy into mass, and you see it here, more or less. So this is something nice just for you to think about, and especially you should think about this equation, because I used it, and this will come for the next lesson. So next lesson will be in stress tensors, So please read about stress tensors because it's a lot of math, and then we'll be ready for radiation eventually. Okay, stress tensors is something new for you, I think. Hmm? Yeah, so please read it carefully. It's chapter, I think, 8. Okay, if there are no questions, we are done.
Thank you.
לא, עשיתם סטרס.
כן, הוא מניח שאתה יודע מה זה.
כן?
לא, אני לא מניח שאתה יודע, אני מניח
שאל
שתקרא.
על יחסות. מניח שאתה קורא.
לא, כאילו אמרתי על היחסות, לא
שאל על יחסות.
מה זאת אומרת, מה השאלה?
כאילו ביחסות כללית, בקורס.
כן.
אנשים שאתה יודע.
אני יודע מתי אתה עושה את הקורס, אבל...